Welcome back to Larry's Classroom. Today we're going to talk about series voltage dividers and parallel current dividers. So we're going to start with the series voltage divider. Say we have three resistors in series. And we have some applied voltage. We'll call that VT. And this is R1, R2, and R3. Basically, this circuit, the VT, the voltage total, will be divided amongst the three resistors here. And if we are interested in knowing the voltage across one resistor, we would like to see how that voltage division happens. Well, we'll start with our Ohm's law, voltage equals I times R. That would be the voltage across any one of those resistors. It'd be the, well, I'll go ahead and draw an arrow for I here. We are not going to calculate I at this point, though we could if we had enough numbers here, enough values. But the voltage across any one resistor will be this current times the resistance of that resistor. And of course the voltage total will be equal to the same current times the resistance total. So this would give us the ability to calculate the voltage across any resistor, and this gives us the ability to calculate the total voltage. You know, so pretty much the same formula. The voltage is voltage total, the resistance is resistance total. But let's work with this thing here. V equals I V equals IR. Now, if we take this formula, any number, if we divide a number by A and then multiply by A, it will be unchanged. If we divide a number by a variable of X and then multiply again by the number X, it will be unchanged. If we take this algebraic expression, which represents a number, IR, if we divide it by 10, multiply it by 10, it will be the same. So what we're going to do with this, we're going to divide this by VT, the voltage total, and we're also going to multiply it by VT, the voltage total. Well, initially this don't look like much, but let's substitute this expression in for VT. V equals, or for the VT in the denominator, I times R divided by, instead of this version of VT, we're going to have I times RT. And we're going to leave this the same, times VT. So, if we're talking about the voltage across any resistor, the current through the resistor times the value of the resistor divided by the current through the loop, which is the same everywhere, times the total current, or by the, which is actually the total voltage, and then times the total voltage, still going to be a good number. So now we're going to notice here, we have, in this fraction here, IR over IRT, we have a common factor, which is the I. So we can throw that away, and we don't change the value of that fraction at all. So now what do we have? We have the voltage equals R times RT, or divided by RT, R divided by RT times VT. Now we have what's called the voltage divider formula. divider, that's right. Voltage divider formula. So what does this formula do for us? We'll circle it. You notice we don't need to use current for that formula. There's no I in that anywhere. But if we wanted to know the voltage across any of these resistors, say we want to know the voltage across R2, the voltage would be equal to R2 divided by R total, which is the sum 1, R2, and R3, times whatever the applied voltage is. So basically what this kind of says is the voltage across any resistor in a series network, and using the voltage divider idea, is this resistance divided by the total resistance gives us a fraction times the applied voltage. So we've derived a formula here. We're going to erase this piece. We'll be using that formula, but I'm going to erase this piece for right now, and I'm going to put some values on this thing here. We're going to say this is 100 volts. And I'm going to put some polarities. R1, I'm going to say is 50k ohms. 50k ohms. R2, I'm going to put that down below here. 40k ohms. R3 is 10k ohms. I'm going to erase this piece and write it underneath so it's a little bit easier to see. 50k ohms. So we got R1 50k ohms, R2 40k ohms, R3 10k ohms. Now if we want to know the voltage across any of these, I'm going to put that voltage divider formula back up here. The voltage equals R over RT times VT. First of all, let's calculate RT here because we're going to use that repeatedly. In this case, RT is equal to 50k. Now let's do it a little bit bigger than that. It's going to be V1 plus V2 plus V3, or R1 plus R2 plus R3. So RT equals R1 plus R2 plus R3 in this case, and R1 is 50k ohms, 50k ohms, plus R2, which is 40k ohms, 40k ohms, plus R3, which is 10k ohms. And you'll notice that 50 plus 40 plus 10 is 100k ohms. So we have, and VT is 100 volts. So we have RT of 100k ohms, we have VT of 100 volts, we have a formula that uses, and we have all the R's. So we have a formula that allows us to calculate the voltage across any of these resistors without utilizing without calculating the current. We could calculate the current to do that, but this saves us a step. So let's see what the voltage across, we'll say this is V3, V2, V1. Let's calculate each of these. Let's start with V3. Okay, voltage equals, what is R3? We're going to use this formula right here. Voltage 3 equals R3 divided by RT, which is 100k ohms, times VT, which is 100 volts, times 100 volts. So let's put the value of R3 in here, which was 10k ohms. So we have the voltage across 3 is the value of resistance of R3 divided by the total resistance times the applied voltage. Well, the units k ohms cancels here. We're going to just take a little line and draw through those. So that leaves us with 10 over 100 times 100 volts, which 10 over 100 is 1/10, and 1/10 of 100 volts is 10 volts, right? So we've got 10 volts here for V3. Let's do V2. V2 equals 40K, using this formula, the value 40K ohms over 100K ohms for total. So we're looking at how much this piece is of the total resistance. That's what this fraction is. The portion of this, that this is of that. The ratio of this to that. That's a good way to look at it. The ratio of R2 to our total. And again, we got 100 volts applied. 100 volts. And this cancels out the K ohms plus 10. This becomes 4/10. 4/10 times 100 volts. Voila, there's 40 volts. Let's do the same thing for V1. And we'll continue to use this voltage divider formula, which is pretty useful. It saves you some steps a lot of times. R1, 50K ohms. I'm going to leave the units off this time. You see they cancel anyway. Over 100K ohms times 100 volts, which is basically 50 over 100 is 1/2 times 100 volts equals 50 volts. So we have 50 volts here. Let's put that in there too for V2. We had 40 volts. And notice 10 plus 40 is 50, plus 50 is 100. So we see here that V total is again equal to the sum of the voltages in each case, and we were able to solve that particular circuit without calculating the current at any point. Now we could do this circuit by calculating the current. Let's quickly do that. So we got, to get the current, we want to get I will equal VT, the applied voltage, divided by RT, right? Which we have VT of 100 volts, we have RT of 100 K ohms, and voltage and K ohms is going to become milliamps, so we have 1 milliamp. 100. Well, I'm going to write it down. I'm going to write it down here so you see a little bit. I equals VT, 100 volts, divided by 100 K ohms. And we've talked about before, when we divide voltage by K ohms, our units is going to be milliamps. Well, 100 divided 100 is 1, so we get 1 milliamp of current. We'll go ahead and write that here, 1 milliamp. So now let's use, we have another formula we've used a few times. We've used it a lot of times, really. Voltage equals I times R. We've talked about this for voltage drop or IR drop. So let's do this for each one of these. Let's start with V1 will equal I, 1 milliamp, times R, 50 K ohms. And we've talked about before that milliamps times K ohms gives us volts. Well, 1 times 50 gives us 50 volts. And you notice this is the same value that we got here. V2, same 1 milliamp, times a different resistance, which is R2. We're looking for the voltage across R2. We call it V2, is 40 K ohms. And that's 1 times 40 volts. Same thing, milliamps times K ohms gives us volts. V3, same formula, IR, voltage, 1 milliamp, that's the same in all the way through the loop in the series circuit, times 10 K ohms now for R3, and milliamps times K ohms gives us volts. 1 times 10 is 10 volts. And you notice each case, V3, V3, 10 volts, 10 volts. V2, V2, 40 volts, 40 volts. V1, V1, 50 volts, 50 volts. So using the method of the IR drops or the voltage divider formula, both gave us the same answer, which, as we've talked about before, it's good to get the same answer, otherwise our methods can be suspect. Well, let's think about what happens when we only have two resistors in our voltage divider. So we're going to draw a voltage divider with only two resistors in it. We're going to apply 100 volts, and we're going to put 10 ohms, and we're going to put 90 ohms. R1 equals 10 ohms. R2 equals 90 ohms. So if we want to find voltage 1, we'll use our voltage divider formula again. It's going to be R1, right here it is, the voltage divider formula. It's going to be 10 ohms divided by RT. Well, yeah, let's make this correct here. We want 90 ohms. I wrote 9 equals 90 ohms. RT is R1 plus R2, which is 10 plus 90, so we'll write that over here. RT in this circuit is 100 ohms, which you can, 10 plus 90, 100. So we're going to divide that by 100 ohms. And then we're going to multiply it times our VT of 100 volts. And this again, 10 over 100 reduces to a tenth times 100 leaves us with 10 volts. Now, we can repeat this to solve for V2, but when we have only two, if we know one, we can use the voltage total formula to find the other. You remember, in this case, the voltage total would be equal to V1 plus V2. We're going to write V1 10 volts here that we just calculated. We don't know V2, V1, we don't know V2 yet, but we're going to calculate using this formula over here. We could go through the same thing that we just did, put 90 ohms in the top and calculate the voltage across the 90 ohm resistor, which we're calling V2. But we're going to use the voltage summation, the rule that voltage around a loop, around a series circuit, that the voltage drops add up to the supplied voltage. Or sometimes they say that the voltage around a loop adds to 0, and basically we'd say this was plus 10, this was minus 10, this is minus 90, and you get back to 0. But the value, the magnitude of these voltages is the same as the magnitude of this voltages. If we want to go with the add to 0, we have to consider this plus 10, minus 10, I'm going to write there, plus 100 volts, minus 100 volts, minus 90 volts, minus 10 volts, minus 90. Well, we haven't calculated that one, so let's not mess with that just yet. But VT, 100 volts. V1 we calculated to be 10 volts. V2 we don't know yet, but we can keep our equation balanced by subtracting 10 volts from both sides. And we get here 90 volts equals V2. So we'll put that 90 volts up here now. I'm going to put some polarities on here. And in this case, I'm looking at current going this direction. Electron current, electron flow. So if we started right here, we go up to plus 10. Then we drop down by 10, minus 10 gives plus 90. We drop down by 90, minus 90 from plus 90 gives us 0, puts us back to that 0 volts. 0 volts plus 100. Right here it's going to be plus 90. Plus 100. So that's kind of demonstrating what sometimes they say the voltage around a loop adds to 0. The other way to look at it is the magnitude of the voltage supplied, which was right here, is equal to the magnitude of the voltage drops, which we had right here. But with just a 2 resistor voltage divider, we don't really need to do the divider method twice. And I'm gonna erase this because it's kind of messy and kind of start over. We're gonna kind of talk about what happens if we have, well, 2 things. We're gonna talk about what we're gonna draw a circuit. We'll discuss 10 volts, and we're gonna put 1 ohm here. 1 ohm equals R1. 99 ohms equals R2. R1 equals 1 ohm. R2 equals 99 ohms. And we're going to put some polarities on this, minus, plus. And what we're going to do here is we're going to use the voltage divider formula to find out the voltage across R2, which we're going to call V2 again. So we have V2 equals, using the voltage divider formula, the value of R2, which we're trying to find the voltage across, 99 ohms, over, well, our total, let's get our RT up here. RT is 1 ohm plus 99 ohms, 100 ohms. 100 ohms. So R1, R2, 99 ohms. We're trying to find V2. Our total is 100 ohms. We multiply that times applied voltage of 10 volts. Now what do you notice here? 99 over 100, the units cancel, and 99 divided by 100 is just basically move the decimal place 2 to the left, which is basically 0.99, right? And we're going to multiply that times 10 volts. And multiplied by 10, we're going to move the decimal place to the right. So it's going to end up being 9.9 volts. So V2 equals 9.9 volts. What's V1? Well, V1 is the 10 volts minus the 9.9 volts. We'll do it that way instead of doing the voltage divider formula. 10 volts minus 9.9 volts equals 0.1 volt. So V2 equals 0.1 volt. We kind of did the same thing we just did in the last one, but here what we have is a big difference between the resistance of R2 and the resistance of R1. And you notice that almost all of the voltage appeared across the larger resistor, 9.9 volts. That is most of 10 volts. And almost none of the voltage, 0.1 volt, that is hardly anything, appeared across the smaller resistor. So when you have a voltage divider network, we utilize one with only 2 to demonstrate our claim here. Most of the resistors with the highest amount of resistance is going to always have the most voltage. The resistor with the least amount of resistance is always going to have the least voltage. And in this case, being we had 99 ohms and 1 ohm, most of the resistance was right here, so most of the voltage will be there. And that is because voltage equals IR. The formula we've talked about many times. I is the same always, so you can see that the voltages are proportional to the resistances. If we greatly increase the resistance, we're going to increase the voltage. or if we decrease the resistance, we're going to decrease the voltage. So we're going to see in a series circuit, voltage divider type circuit, the most voltage is always going to appear across the largest resistance. The least voltage is always going to appear across the least resistance. And of course, what you probably saw as the advantage of the voltage divider method here is that we did not have to calculate the current, and it can happen that the current might be a clumsy number with a lot of decimal places or something. So it was convenient, basically, and it saves you one step. So it's a good method. Now we're going to move on. We're going to talk about series current dividers. I'm going to write that up here. Series current dividers. Or parallel, excuse me, not parallel. Those were series voltage dividers. We're talking about parallel current dividers. Divider circuits, let's call that. Circuits. So what is a parallel current divider circuit? Well, if we have two parallel resistors, we'll call this R1 and this R2, and we have a current in here, IT. We can see that current's going to divide up into two pieces. It's going to be I1 and it's going to be I2. And of course, it's probably pretty obvious to you by now that IT, the total current in, will be equal to I1 plus I2. And if we had more branches than 2, they would add right in there with it. So we want to figure out what I1 is. Let's kind of go through the derivation of current divider formula. Well, Ohm's law tells us that current is equal voltage divided by resistance. So I1 is going to equal to the voltage across this thing divided by R1. Right? I think that's probably easy enough to understand. Now, how could we find the voltage across this thing? We have a formula that says voltage equals I times R. So, if we wanted to find the voltage here, I'm going to put a line here, IT is going in that direction, so basically we're negative and positive here because we're doing electron current flow. So if we want to find the voltage across this network, if we have IT and we have our total, we can come up with the voltage using this. Well, we don't have our total, but we have a formula for our total. For two parallel resistors, our total is equal to R1 times R2 over R1 plus R2. And we have this guy here. So if we want to know the voltage here, the voltage across this unit, the voltage, I'm going to call this voltage total, voltage is going to be I total times R total. The voltage across this network will be this total current times this equivalent resistance. So we're going to work forward with that. We're going to try to find that voltage. So that voltage across this network, which I guess I'm going to say V applied from here to here, will be, using this formula, it's going to be Vt equals It, which we're given in this type of problem. We don't know RT, but we have a formula for find it, and we'd be given R1 and R2. That would be R1, R2 over R1 plus R2. Here we've got the I times the R. We're interested in finding I1. We have this I equals V times R1. So I1 will be V divided by R1. So being we have here Vt, which is what we're interested in, I1 is going to be Vt actually here. I'm going to call it Vt. It's the only voltage we're going to have in this particular circuit, but nonetheless. The current I1 is going to be this V, let's call that Vt, so we're consistent. It will be this Vt divided by the value of R1. We have here an expression that represents Vt. If we divide that by R1, that will give us I1. So let's say that I1 we're using this formula, but we're substituting in this value for Vt is It times R1 R2 over R1 plus R2, but we have to divide it by R1, so we're just going to go a divide symbol for right now, divided by R1. So here we have an expression to represent this I1 that we're trying to find. I1 equals I total times R1 R2 over R1 plus R2, which was our parallel resistance formula for two parallel resistors, divided by R1. So it's basically current times resistance, voltage divided by resistance. Well, we're going to invert this R1, so we're going to go down one more step. I1 equals It times R1 R2 over R1 plus R2, and we can divide by multiplying times the reciprocal. So that's going to be times 1 over R1. Now what do you notice here? In this expression here, we have a factor of R1 in the numerator, or in the denominator and in the numerator. So we can cancel those two factors. So this comes down to It times R2 over R1 plus R2. And there's little times in here. Now I'm going to change the order of these. Multiplication is commutative, so it don't matter. So we come up with a formula like this. I1 equals R2 over R1 plus R2 times I total. So now we have what we call a current divider formula. Let's write that here. Current through this branch here is equal to the opposite resistor divided by the total resistance, or by the, not the total resistance, but the sum of the two resistors, times the applied current, times the total current. So, and basically, because of this guy here, less current will go down the larger one and more current down the lesser resistance. And of course, we could go through the same thing that we just did to come up with I2. In this case, I2 would be equal to instead of R2, it's going to be R1 divided by the R1 plus R2 times IT. Now I'm going to erase some of this, and we're going to do some work with a few of these. We derived, I might leave that down there. We derived two current divider formulas, which I'm just going to leave right here, down here. I1 is the value of R2 divided by the sum of R1 and R2 times applied current. I2, the current through R2, is equal to the value of R1, the other resistor, divided by the sum of the two resistors times the total current. So I'm going to put a couple values on here. IT 20 amps. $20 amps. I'm going to say that R1 is equal to 4 ohms. And R2 equals 6 ohms. And we're going to use these current divider formulas that we have just derived to calculate the currents through each R1 and R2. Well, I1 equals R2, I'm going to just copy it up here, R1 plus R2 times IT. So now we're substituting our given values. It's R2. We're trying to find I1. So I1 equals, what is R2? That's 6 ohms divided by 1 ohm, or 4 ohm, R1, plus 6 ohms. We're going to multiply that times IT of 20 amps. So we have here ohms, ohms, ohms. They can all cancel. That becomes 6 over 4 plus 6 times 20 amps equals 6 over 10 times 20 amps, which will equal 12 amps. 6/10 times 20, 12 amps. That gives you 120 divided by 10, so it's 12 amps. So we have determined that I1 equals 12 amps. Let's use the other voltage divider or current divider formula to calculate the current I2. I2, I'm going to write the formula right here above so it's a little easier to look at, equals R1 times R1 plus R2 times IT. Now notice again that we're trying to find I2. The numerator of the fraction is the other resistor, R1. The denominator of the fraction is the sum of the two resistors. This is our current divider ratio. So we're going to put in some values here. R1, that is 4 ohms. R1 plus R2, that's 4 ohms plus 6 ohms. We're going to again multiply by IT, which we're given, 20 amps. Again, the ohms all cancel, gives us with 4 over 4 plus 6, which is 4 over 10, times 20 amps. And 4 over 10 times 20 amps gives 8 amps. And you will notice that I1 plus I2 is equal to I1, 12 amps, plus I2, which was 8 amps, and that's going to be equal to 20 amps. 8 plus 12 is 20, which is equal to IT. So once again, we see that the currents split up and they sum back together, but the sum of the current in each branch is equal to the total applied current. We wouldn't have actually had to have calculated the second one. We could have done we could have said that IT equals I1 plus I2. We could subtract I2 from both sides. We'd have IT equal IT minus I1 equals I2. And then we could put in our known values. We would have said 20 amps minus I1, which we found to be 12 amps, equal 8 amps, which would be equal to I2. So we could have calculated it using the current summation formula, and we would have gotten the same answer. You might have noticed that the current divider formula is kind of the inverse of the voltage divider formula. We're going to kind of put these up side by side and take a little quick look at that. We did a voltage divider example starting out the day. We had VT. Let's move that over to the right just a little bit. VT, and we had two resistors, R1, R2, R1, R2, and we basically said that the voltage across, we'll use R1 in this case, V1 is equal to V1, or no, R1, excuse me, divided by R1 plus R2 times VT. There was our voltage divider formula. We had our applied voltage. We multiplied that times the value of this resistor plus the total resistance, the ratio, and that gave us the voltage here. Now we're going to look at, review quickly this series, or the parallel current divider formula that we just saw. Then we were given a IT, in this case, total current. We were given an R1, we're given an R2, and we're interested in I1, which went this direction, well, IT in I2. So we're using our current divider formula. We discovered that we could find I1, the current here, by taking, this is R2 here, the other resistor in the numerator over the sum of the two resistors, and multiplying that times the IT. And you can kind of see here some corollaries instead of currents, we're using voltage total in the voltage divider, and in the current divider we use current total. And you notice that we have the total resistance, or the sum of the two resistors in the denominators of both of them. The main difference here, you see that to find I1, we put the value of R2 in the numerator. To find V1, we put the value of V1 in the numerator. So basically, kind of what this says, because think about this, R2 is equal to R1 plus R2 minus R1, right? And yeah, I don't like that. Let's leave that out of there. I might confuse you with that. As this becomes bigger, as this resistor becomes bigger, the current through this one becomes greater. As this resistor becomes larger, the voltage across this resistor becomes larger. So the voltage is directly proportional to the resistor which you are measuring the voltage across. The current is inversely proportional to the resistance of the other resistor, or as the other resistor gets larger. No, that ain't right either. It's directly proportional to the resistance of the other resistor, but it's inversely proportional to its own resistance. As we make R1 smaller, R1 will become a lesser portion of this, which will make this denominator get bigger. So the voltage divider formula, voltage is directly proportional to the resistance. The current divider formula, current is inversely proportional to the resistance in the branch. That's what I'm trying to tell you. One more thing I think I want to talk about before the day is over. We're going to kind of look at what happens when there's a big difference between the value of the two resistors in a parallel branch, in a parallel circuit. So we're going to draw another current divider type formula. Current divider type circuit, I mean. And over here we're going to say R1 equals to 1K ohm. R2 equal to 999K ohms. And we have IT, a total current going into this thing of 1 amp, which is also equal to 1,000 milliamps. Now we're interested in how this current divides up. So let's look at I1. We use the current divider formula, which I'm going to write it up here again. I1 would be the other resistor, R2, over the sum of the two resistors, R1 plus R2, times IT. So we're going to figure out I1. We're going to put some values in there. I1 equals R2 999K. And that's going to be over the sum of these two. Well, 999K plus 1K is 1,000K. So we're just going to go straight to that step. R1 plus R2 is 1,000 K ohms. The current, 1,000 milliamps. So we could look at some cancellation, but 1,000 into 999, the units here cancel, so it was 0.999 times 1,000 milliamps, which multiplied by 1,000, remove the decimal place 3 places to the right, so it's basically 999 milliamps. So we got I1 equals 999 milliamps. Now you might notice that this small, much smaller value of resistance ended up with almost all of the current. We're going to calculate I2. We're going to go ahead and do it with the voltage divider formula, though we could use the current summation formula, or the current divider formula. We could use the current summation formula, but we're going to go ahead and see what I2 is. We want I2 here. I2, that's going to be the other resistor, 1K ohm. Over the sum of the two resistors, which is going to be the same as before, 1,000 ohms, or 1,000 K ohms, and by the same total current of 1,000 milliamps. Now this fraction, the K ohms cancel, which is 1 over 1,000. 1 divided by 1,000 equals 0.001 times 1,000 milliamps, which is 1 amp. Well, multiply by 1,000, we move the decimal places 3 places to the right, so we end up with 1 milliamp. So I2 equal 1 milliamp. So we did pretty much the same thing we did on one before, but in this case we had a way different value. Some of them were closer. This one we have 999 times as much resistance as that one. And what did we notice? That almost all of the current went through the smaller value resistors. This high value resistance took very little of the current. If we took it out of there, say it was gone, we're going to just kind of imagine it being gone. I'm not going to actually erase it. Well, yeah, I'm not going to erase it. But if we imagine it gone, what would we have then? We would still have R1 equal to 1K ohm. But we would now have I1, same applied current, equal to 1,000 milliamps. So the effect of putting this 999 K ohm resistor across the 1K ohm resistor is we changed the current in the 1K ohm resistor from 1,000 milliamps to 999 milliamps. We only made a 1 milliamp change in the current by putting this large resistor across there, which, as you learn more about metering, you know, reading voltages, this is why a voltmeter is designed with a large resistance, so it doesn't change what's happening in the circuit very much when you put the resistor, when you put the leads across there. And 999 compared to 1 is a very large value, and it made a very small difference in the current through R1 by applying that to there. Anyway, I think that'll do for today. I appreciate you coming back, and be sure to like and subscribe. Until the next time, keep on learning.